Hey, let's start off with some sample diploma problems. Which of the following statements best described the total measured mass is represented on the left side of reaction 2 compared to the measured mass on the right side? Okay, so whenever you're doing a nuclear equation, this side is always heavier and this side is always lighter, no matter if it's fission or if it's fusion. So the left side is going to be greater, and because energy equivalence of the mass defect. Okay. There we go. The energy equivalence of the mass of one alpha particle. So that's just E equals mc squared. And if you look up the mass of an alpha particle on your data booklet, it tells you that the mass of an alpha particle is 6.65. 6.65 times 10 to the negative 27. And then we multiply that by the speed of light squared. Get rid of that extra decimal. I don't know where that came from. And you get 5.99, 985 times 10 to the negative 10 joules. And this one's a little bit tricky with rounding. Yep. So we'd want to do this, which would bring this up and would bring us to 6.0 times 10 to the negative 10. So 6010 would be the correct answer. Okay, which of the following statements best describes the collision between the neutron and the nucleus where the neutron is absorbed? So I think we need to read here. So the neutrons are then directed at the sample. If a neutron is absorbed by the nucleus will form a new unstable isotope that is in a higher energy state than the original nucleus. So it says that the neutron is absorbed, right? So it looks like we have this super fast moving neutron, and then we have the nucleus, and it's absorbed, right? To me, that doesn't sound like it's an elastic collision, because this has a lot of kinetic energy, and then it's absorbed, and this isn't going to move very much. So to me, it sounds a lot like the collision is inelastic, and the kinetic energy of the system is not conserved. With this one, the reactions when listing in increasing order of energy, so that's from low to high, would be. So you have to be able to identify, this one's chemical. So that's going to be our lowest. That's just a combustion reaction, right? And then we have small getting bigger. So this is fusion. And this is big getting smaller. So this is fission. And it's released per unit mass, so per gram or whatever, per kilogram, like that. So that means that fusion is going to be the biggest, and fission is going to be in between. So 231 is the correct answer. The energy released from reaction 3 expressed in scientific notation, so it gives us all of this. Okay, so let's calculate that. So we need to add up the mass of our reactant. So we have a neutron behind here, which is 1.674927 times 10 to the negative 27. And then we also have uranium, 235, which is 235, which is 3.902996 times 10 to the negative 25. Okay, so that's the total mass of my reactants. And then I add up the mass of my products. So we have the barium, which is 2.339939 times 10 to the negative 25. And then we have the krypton, which is 1.526, 0.470 times 10 to the negative 25. And then we have the 3 neutrons. So I would go start a bracket 3 times 1.674927 times 10 to the negative 27. And if I did it right and I didn't make any mistakes, they should be close. Oh, perfect. So those are really nice and close. So then I just take my heavier one, my reactants, and subtract it from my products. And I end up getting this. This is my change in mass. And then once you find your change in mass, right, it's just E equals mc squared to convert it over to energy, and that's what it's looking for. So I'll take this, and I'll multiply it by the speed of light squared. And I get 2.8 times 10 to the negative 11. So 2811. Okay, energy is released in this nuclear fusion reaction because I don't even need to read it, right? I know that fusion comes from a mass, so the mass of the alpha particle and the neutron is less than the mass of the intermediate product. Yeah, changed mass. The reaction 1 above is classified, so this reaction 1, hydrogen turning into heavier hydrogen, is fusion, because since small nuclei make a larger nucleus. A is definitely the answer. And then this guy here, which of the following rows matches the energy per nucleon for the fission and fusion reactions, right? So it looks like this fission gives off more energy than the fusion, but we have to look at it in terms of per nucleon to really make it fair. So this has 3 nucleons before, 3 nucleons after, so it looks like 3 nucleons is how many we have. And this has 236 nucleons. If you add up these ones, it's 236 as well. So we have to divide this by 236 because that's how many nucleons we're using in that. And if you do 5.49 divided by 3 and 204 divided by 236, you'll see that the fusion gives off a little bit more energy, 1.83 compared to 1.864. 866. That's weird. That must be a typo. But it looks like I changed something. That's why the font's all weird. Interesting that it doesn't get you the same answer. 236. Yeah. Anyways, but B is supposed to be the right answer. Okay, so let's do a lesson about half-life. So perform, this is important, non-logarithmic half-life calculation. So if you've done half-life in Math 30, these are non-logarithmic, which makes them a lot easier, which kind of means you're not really changing around a formula or anything like that, because you don't need Math 30. It's a co-requisite, not a prerequisite to this. So radioactivity. So radioactivity is a spontaneous event, meaning that when a nucleus decays and releases alpha, beta, gamma, this is particle, but gamma is not particle. And I guess if you think of it as a photon, it is. The exact timing of when the next particle is going to be released is unpredictable, right? So you don't know when it's going to decay or not. But what you do know is if you have a large number of nuclei, right, a large number of decays, the more you have, the better the probability is going to be that it's going to happen. So while the individual event is unpredictable, we can statistically predict when a large number of decays will occur with good probability. So radioactivity is measured by the number of nuclei that change or decay in a given period of time. So 1 unit, there's really no standard unit on the diploma, but 1 is becquerels, and that's decay per second. So what I mean by this, I'm going to open this up. This is a fun little game that we play. You could turn this into a gambling game. Just wait for it to open. Almost there it is. Okay, so this is our buckets O plutonium, right? We can do any atom we want, and we can adjust this half-life, which we haven't really talked about what it is, right? So what I can do is I can add, I'm just going to pause, is I can add a whole bunch of nuclei, right? So what I do in class, just let me write on it, no. What I do in class is I give names to each one, so you can pick any nuclei that you want. Last person to decay wins. So I am going to pick this one as me, pick another one as you, but where my mouse is going to be me, and we'll see who the last one standing is. Have you decayed yet? I'm still alive here. So it is randomly decaying. We don't know when it's going to happen. I'm still alive. I'm going to win. Right, and Becquerel's talking about a decay per second, so how many of these happen? So you can see that there's less and less, and there's less decays happening. Come on. It's taking forever. Oh, 2 more decayed. I'm still alive. Oh, the one beside me decayed. We're gonna do this till the end. You're probably all skipping ahead in the video for this part. I want to see if I win. I've made it this far. Come on. Oh, I'm out. Right? So we can see who the last one is remaining, right? It's kind of random when they decay. We don't know when it's going to happen. And we saw a lot more decays when there was more at the beginning. I think I made the half-life just a little bit too long. That one's gone. There are 3 left. I kind of want to see who wins. I'm going to make the half-life shorter next time. Come on. This is a very exciting lesson. Oh, there we go. That's our winner. So that's the last one left. Okay, so I'm going to reset all my nuclei. I'm going to make the half-life a little bit shorter. And now I'm going to let them decay. Right, so you can see tons of decays happening at the beginning, but after a while, less and less are decaying. And our winner from last time was like that one and this one, but they're totally different this time, right? Every time I do this, it's going to be different, and we'll have a different winner because it's totally random when they decay. But what's constant is the half-life. So we'll talk about what half-life is. We'll reset them. If I set it at 1. So we have, pause. So how many did I add? I added 50. Let's reset all. So if I add, let's pause. There we go. 1, 2, 3, 4, 5. Right? So I added 50. So what our half-life is, so our half-life is right here. We don't know when each individual one is going to decay, but we do know when about half of them will decay. So when I hit this point, it should be right at 25. Okay, so there we are at a half-life. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. So we've reached about half of it, right? And then if I keep on adding more and more and more, what it's going to be is it's going to be more accurate. So if I add 100, our half-life, we should have 50 left. So it's just how long it takes for half of them to be gone. And if you have enough atoms, the more accurate it's going to be. When you have less and less atoms, the less accurate it's going to be, right? Because if I just have, let's reset, let's just add 2. There we go. Right? At the half-life, we should have 1 gone. Yeah, it's pretty close. And then I do it again. This time, my half happened right here, and then my other one decays at a very different time, right? So the more you have, the more accurate it's going to be. So the activity of any particular sample, so activity meaning how much it decays, depends on the total number of nuclei present. So for any given isotope, the more nuclei, the greater the probability is that the nucleus is going to decay. Okay, so when a sample decays, the total number of nuclei is decreasing, so activity increases over time. The number of decays per second will decrease over time. But what remains constant is the half-life, the time it takes for a sample to decay to half its amount. So we can show this in a graph. So a plot of decreasing activity shows the activity or total number of nuclei decreases by half for every half-life. So if there's 100 nuclei present, after one half-life you would have 50, after another there'd be 25, and so on. Right? So this is what a graph looks like for half-life. Right? We start off with 100. At our first half-life we have 50. At our second we have 25, so half of that, and then half of 25 is our next half-life, which is 12.5. So that would be after 3 half-lives. So that's how you would represent it in a graph. So each isotope has its own characteristic half-life. The more stable you are, the longer you last. The less stable you are, the shorter it is. So with times ranging from a microsecond to million of years. So carbon-14, the half-life is 5,730 years. It's a very long time, while polonium is 1.64 times 10 to the negative 4 seconds. So very, very unstable. Carbon-14 is pretty stable. So these are different isotopes. So uranium-238, that's its half-life. Uranium-235, uranium-234. Obviously, this one is the most stable. This one is the least stable, but they still have a really long half-life. So when the rate of decay is proportional to the amount of material present, we have a logarithmic or exponential relationship. So this is the formula that we get. N equals N naught. That's what the 0 is. 1/2 to the N. So N naught is our original amount, and it can be like a decay. It can be a becquerel. It can be a percentage. I'll show you both. N is the amount remaining after a time period, and the little n is the number of half-lives over a period of time. So this little n, they don't give us a formula for it, but this is important. So this is a formula you have to kind of memorize. I don't know why they don't give it to you, but they don't. So to find n, you just take your time divided by the time for your half-life. So if my half-life is 10 years and the time is 4, then I have undergone half a half-life. Okay, so T is the time for the decay, and T half-life is the half-life of the element. And you have to make sure that they're in the same units. Okay, so let's do an example. Phosphor-32 has a beta decay half-life of 14 days. If a 500 millicurie sample, so this is just a way of measuring decays. You don't even have to worry about the units in this. And it was purchased November 13th. How many millicuries of activity would be available at Christmas 6 weeks later? So I got you some Phosphor-32 for Christmas. I want to know how many half-lives have happened, what it's going to look like. Okay, so it's got a half-life of 14 days. So we can use that first formula. So we have 6 weeks, right? So our time is 6 weeks. But we can't keep it in weeks because this is, I guess we could actually, we could keep it in weeks. Let's keep it in weeks, that's easier. The half-life is 14 days, so it's in 2 weeks. As long as they're the same, it's fine. So how many half-lives have occurred? N equals 3. We've had 3 half-lives. For a question that's a nice even number like this, we don't actually need to use the formula, right? What we can do is this. So at 0 half-lives, we're at 500 millicuries. Right? After the first half-life, there's going to be half that, so 250. After the second half-life, there's going to be half of that, which is 125. And the third half-life, right, is going to be half of this, so it's going to be 62.5. So this is my answer, and this is how you can do it without the formula. So if you ever get a nice even n where it's not 0.0, just do it that way. It's really nice and easy. And it asks us to graph it out. So this is 1 half-life, this is 2 half-life, this is 3 half-life. So this is 500, this is 250, this is 125, and this is 62.5. Right, so we start up here, we go here, and then here, and then here. So this is what our graph looks like. So based on the chart, determine the time required for a 40-gram sample to decay to 125 grams. Okay. So what this can tell us really well, so this is 100% of our sample. This is our starting point right here. And this is 50. This tells us our half-life, right? So if we just find out where it touches there, and we go down. So it looks like our half-life is 0.6 hours. So that's important. Well, how many half-lives have occurred to get to 125? Well, this is in percentages, this is in grams. But what we can do is we can do that same thing I did before. So at 0, half-life sits at 40, that's our start. After our first half-life, it's going to be 20. Our second half-life is 10. Our third half-life is 5. Our fourth half-life is 2.5. And then our fifth half-life, we're at 1.25 grams. Look at that. So for us to get to 1.25 grams, we must be at 5 half-lives. And n equals time over the time for my half-life. Well, move t1 half up here. So the time for my half-life I found from the chart was 0.6 hours. I have undergo 5 half-lives. So what's my time? Well, it must be 3 hours. Okay. There's other ways of doing that, but I think that's a pretty easy way of doing it. So, yeah. So radioactive isotopes are used for science research and medical work when chemicals are needed to be tracked inside the test tube or the human body. A radioactive isotope is substituted for normally non-radioactive one. So an example of that is if you wanted to follow the phosphate molecule in ATP, which gives energy for cells, you can substitute radioactive phosphor 32 for normal phosphor 31, and it leaves a radioactive trail which you can track and you can see where it goes, so you can see how phosphorus is switched around in the body. So here's an example. 40 units of radioactive iodine are injected into a person before an X-ray. So they want to sort of see where this is going. The half-life of iodine is 2.5 hours. After 5 hours, a 10 milliliter sample of blood is withdrawn, showing an activity of 0.01 units. What is the total volume of blood in the patient, and how much total activity would remain in the person after 4 days? Okay. So they start off with 40 units, and then the half-life is 2.5 hours, and then they did 5 hours. Okay, so that's, so we can figure out this first one, right? So n equals time over t1 half, right? So half-life is 2.5 hours. And 5 hours goes by, so it must be 2 half-lives, right? So if we start off with 40 units in the body, after 1 half-life we'll have 20 units, and after 2 half-lives we'll have 10 units. So this is how many is in the body. And this part of the question here is a little bit tricky. So they want to know how much blood is in the patient. So they found 0.010 units in the person, but that was only from a 10 milliliter blood sample. So what you can do is you can sort of do a cross multiply and divide here. We know that they have a total of 10 units in their body. So if we cross multiply and divide, we can find out how much total blood is in the person. So if I go 10 times 10 divided by 0.01, we end up getting 10,000 millimeters, or 10 liters of blood, which is about double. Normal people have about 5 liters of blood, so this must be like Andre the Giant or something like that. Just a really big dude if there's double the amount of blood as a normal person. Okay. How much total activity would remain in the person after 4 days? Well, 4 days is a long time when the half-life is 2.5 hours, so I don't want to do this whole chart. So this is one that I would want to use the formula for. So first thing I need to do is find out, well, how many half-lives are taking place after 4 days? So I'll keep them both in hours. So the time for my half-life is 2.5 hours. And I have 4 days. And then there's 24 hours in one day. So now everything's in hours. So 4 times 24 divided by 2.5. So 96 hours in 4 days. And I divide it by 2.5. And I get 38.4. So I've undergone 38.4 half-lives. As soon as I have a point something, I have to use that formula. Okay, I'm going to use n equals n naught half to the n. And my original, I start off with 40 units, and I undergo 38.4 half-lives. So how I would type that into my calculator is I'd start off with the half to the 38.4. And then I would multiply it by my 40 units. So how much is left in their body? 1.1 times 10 to the negative 10 units, essentially nothing. Right? And that's why they use radioactive iodine, because it has such a short half-life, because you don't want people having radioactive substances in their bodies for a long period of time. So there's essentially nothing left, 0.00009 times. Yeah, it's all gone. So safety considerations. So, tracking someone, tracking where stuff goes in the body, you have to weigh safety considerations. This sentence doesn't make sense. These considerations must sometimes be weighed against each other. What considerations? Well, for example, to do an iodine blood test, longer half-lives are not desirable because the retention of radioactive iodine in the blood would be hazardous, right? So you don't want something that has like a 3-day half-life because it's going to stay in you for a long time. And what type of radiation, alpha, beta, or gamma, would be best to use on humans? Well, if you have alpha inside of you, it can be close to your DNA and it can cause a lot of damage, and it also has a bad penetrating ability. So it wouldn't be able to be like get through your skin to be tested. So alpha would be bad, right? Beta would be a lot better because beta is really tiny. It doesn't it doesn't have a lot of charge. It's not very big, so it wouldn't be ionize your DNA as well. It wouldn't be damaging to your DNA, and it can get through your skin. So a beta emitter is really good to use, and then a beta emitter with a short half-life would be something that you'd want to use in human body. So another use of isotopes is dating objects. So the best example is carbon dating, which you've probably heard of. Whenever I think of carbon dating, I think of young Justin Bieber. Made this a long time ago. Dating carbon, but no, it's dating as in how old something is. So with carbon dating, the radioactive form of carbon-14 is mixed with the non-radioactive carbon-12 in the air, and the ratio of the two isotopes is relatively constant, right? So there's always more 12 than 14. So when an organism is alive, you're constantly exchanging carbon, right? So you breathe out CO2, you take in carbon with hydrocarbons that you eat, carbohydrates, and you're always exchanging it so that stays constant. But when you die, you no longer breathe out CO2. So whatever carbon is in your body when you die stays the same. And if you leave someone for long enough that's dead, right, what's going to happen is the carbon-14 is going to decay and the carbon-12 stays the same. So the longer something has been dead, the less carbon-14 is in it. And I said before that carbon-14 has a half-life of about 5.7 thousand years. So we can estimate the age of a dead organism by the amount of decrease in carbon-14. So when you're radioactive dating something, if you're using carbon dating for a dinosaur, well, that's not very good because dinosaurs lived 65 million years ago, and the half-life for carbon-14 is only a few thousand years. So that's too many half-lives have happened, and you wouldn't be able to detect the carbon-14 anymore. So the half-life determines the range of applicability for any given isotope. So for instance, carbon dating is good for up to about 10 half-lives, so 60,000 years. After that, you wouldn't be able to detect it, right? So if you were looking at dinosaurs, you'd want to use these guys, because that would be better for dinosaur bones. Okay, there's your half-life questions. If you have any questions, let me know.